Okay, let's move to the next section. So this is basically cover the discrete signal part. So discrete signal part, discrete signals. So up to now, we basically discuss almost all the type of continuous signal. So we found that this is a very simple example. So we have a time domain here, and this is your xt. So we define it as a kind of a continuous signal. For example, from 0 to t naught. So within the period of 0 to t naught, so your function is basically continuous. You can't see any discontinuity in between 0 and t naught. So this is kind of a continuous signal. So then we define that t is a kind of a continuous random variable, and x is the function which is depends on t, and here this t is a independent random variable, which is a kind of a continuous variable again, and this is the dependent random variable. Again, it's also kind of a continuous function. So these type of signals we basically discussed during last couple of sessions. So how do we apply Fourier series? Fourier series for this kind of xt's where you have kind of a periodic type of functions, periodic with t, which is 2 pi omega equals 1 over f, which is in frequency Hz. So then we move to the Fourier transform. So in that case, we found that we can easily get the Fourier transform for this xt, which is a kind of a periodic type of function, where this t goes to infinity. So we basically consider this kind of pulses. So it's basically non-zero for a certain time period, rest the functional value is 0. So we basically start with these periodic functions and explain what is actually Fourier series. So then we move to the periodic type of functions by letting this period t to be moved to the infinity. So then we come up with this Fourier transform. So whatever this Fourier analysis is basically done for the continuous signals. Okay. So if we basically go through this very important set of equations, we found that xt equals sum of k goes from minus infinity to plus infinity ak e to the power j k omega naught t. So this is the Fourier series definition of xt. So these are Fourier series coefficients, Fourier series coefficients. Okay, and ultimately we express this xt, which is a kind of a periodic function in time domain, to kind of a finite to infinite sum of complex exponential terms. So those are the complex exponential terms. So those are the complex exponential terms. So the contribution of this each exponential term is simply defined by this prefactor, the coefficient ak. So those are known as Fourier series coefficients. So we can basically evaluate this Fourier series coefficient like this: xt e to the power minus jk omega naught t dt. So this omega naught is actually 2 phi over the period t. Okay, so this is actually the Fourier series discussion. So if you have a kind of a periodic function, so then we can simply expand it to kind of finite to infinite number of complex exponential terms. So then we move to this Fourier transform, so which is actually like this. X e to the power j omega t omega and x omega equals minus infinity plus infinity xt to the power minus j omega t dt. So then we define this xj omega or x omega as the Fourier transform of xt. So in some textbooks, this is basically referred like this: f curve bracket xt is x omega. So the Fourier transform of xt is capital X omega. So then this is a kind of a time domain quantity, and this omega is representing this frequency domain. So this is actually the inverse Fourier transform of x omega. So we can simply say that equals xt. Okay, so this is the base discussions we had during last couple of sessions. So if you have a kind of a continuous signal, so we can basically translate this properties from time domain to frequency domain by applying either Fourier series or Fourier transform. So later on we found that Fourier series is basically defined for a kind of a periodic function or kind of a function like pulse. So then at the same, during the same discussion, we found that, so if we basically develop a kind of a periodic function using the same pattern, so we can easily derive the Fourier series coefficients of this periodic pattern, which we basically derive from this periodic shape through the Fourier transform of this X. So these are the stuff we basically discussed during last couple of sessions. Now we are planning to move to the discrete domain. So now we are planning to move to the discrete domain. So discrete domain. So it means like So this is the continuous function xt. So this is the discrete function. So see the difference here. So the x-axis is basically here t, which is a continuous variable. But once you map it to the discrete signal, so your x-axis would be n, which is a discrete variable. So this n can basically take 0, plus minus 1, plus minus 2, plus minus 3, likewise plus minus 8. So we can take integers. So n is actually integer. N is actually integer, and it can basically take any integer value from minus infinity to plus infinity. So for this particular case, so we have x0, we have x1 and x5. So the simple difference here is actually for this case we have continuous variable t appear here, and now we have a discrete variable n, which is a kind of an integer appear here. So now this is the discrete signal. So this is discrete signal. So this is discrete signal. Yes. So now we know that if it is what's the simple difference between xt and xn. So xt is a continuous signal. So if you basically define a range of t, so this function is continuous within the defined limit. But once it's come to the discrete signal, so your x-axis would be a kind of a discrete variable, which is defined by or represented by n. So n is a kind of an integer value that n can basically take any values in between minus infinity and plus infinity, but those values are basically set of integers. Okay, so we can define this discrete signal in 3 different ways. Discrete signal. So one is actually a graphical form. So like this. 1, 2, 3, minus 1, minus 2, minus 3. This is 2. This is 1, 0.6, 0.5, 0.6, 0.5, 1. So this is the graphical representation of this discrete signal. So this is xn, so this is n, and this is actually xn. So we can basically graphically illustrate these samples, discrete samples in this 2D plane. So x-axis would be basically n, discrete random variable, and y-axis is the amplitude of this each and every discrete sample. So for example, here this is x0. So the x0 is actually 2, x1 is actually 1, x minus 1 is actually 0.6. Likewise, you can define this function. So this is the graphical form of representing any discrete signal. So similarly, we can explain any analog or continuous signal using discrete graphical form as well. So the second is actually kind of a mathematical mathematical form. Okay. So for certain functions, it's hard to define it we can define the function mathematically, but the issue is like, so the whatever the definition would be pretty much complex. So for we'll take one example, then you may realize. So this is a kind of a function. So the rest is actually zero. So this is the function xn in discrete domain which we need to define mathematically. So how do you define this function mathematically? So we can start with like this. Xn equals, so we know that this function basically take two values. One is 1, the other one is 0 basically. So 1 and 0. So we can then define the range of n which this function values are basically 1. So we can simply say that n equals 0, 1, 2, 3. So this is otherwise. So this is a way of representing this xn using a mathematical form. Or else we can do like this. So we can replace this each and every sample using a delta function or kind of a unit impulse function. So we can represent this first sample using delta n, second sample delta n minus 1, third sample delta n minus 2, fourth n minus 3. So this is again another way of modeling your discrete function or discrete signal using a mathematical way. So once it comes to, okay, then again we can do kind of thing. So this is also equals to u n minus u n minus 4. So un here is a unit step function in discrete domain. In discrete domain, you know that unit step function in a continuous domain, which is equals to this. So this is ut. The value is 1. So once it comes to the discrete, so you have discrete samples from 0 to infinity, n equals 0, 1, 2, and 3, so on up to infinity, and the magnitude are basically 1. So then un is this kind of a function. So this is n 0, 1, 2, 3, 4, and these are, so this is un. So similarly, this is actually a unit impulse function in discrete domain. So we know that this is delta t is the continuous function in function in continuous domain. So the respective discrete form is delta n. So this is again defined t equals 0. So this is basically defined at n equals 0. So nothing different. Here the area is actually 1, the amplitude is infinity. Here the so we cannot define an area, so here the amplitude is actually 1. So nothing else, but these two functions are basically defined at 0 point. So delta n is a unit impulse in discrete or discrete domain. Un is the unit step function in discrete domain. So basically you can define any kind of a discrete form of a signal using either a kind of a unit impulse or unit step. So for example, if we take one more example, so this kind of example, this is n, this is 1, 1.5, 1.5, 0.5, 0, 1, 2, 3. So for example, so this xn can be written as this. So using this unit impulse, this is unit impulse function. So this is the way we can mathematically model any kind of a discrete function. Either you can use this first format with a big bracket and differentiate this whatever the different values that discrete signal is basically taken. So then you can define the domain or the values of n, these discrete values corresponding to these discrete values. So then the other way is like depending on the function you can write the discrete function using either unit step functions in discrete domain or unit impulse functions. Yes. So the third format is actually using a kind of a vector form. Vector form. So if I want to write it in the vector form, so this function, so I can simply say that xn equals 1, 1.5, 1.5, 0.5, 0, input arrow. So this arrow basically represents the origin. N equals 0 point. Because we know that this n can basically take some values from minus infinity to plus infinity. So if we just put some values like in this vector form, so it never give a kind of a proper idea about the original discrete signal. So then we should specify where this origin is. So for example, so if you have a function like this, so then what happens? So if you ideally can say like this, 0.5, 1, again 0.5. So see, like, so without this arrow, so you cannot redraw or draw the this discrete function, or you can't represent this discrete function using graphical form because you don't know where this origin is. So if you put like this, you know that this is actually n equals 0. So then you can basically identify this value as the value for x1. So then you can treat this as x minus 1 and x1. So without this arrow, you cannot precisely explain the discrete signal. So now we basically identify three ways of modeling this discrete signal. One is this vector form. So we can basically place the amplitude inside this curve bracket and mark the origin using an arrow. So the second form is you can use this mathematical method. So when we are using mathematical method, either you can use this direct delta or the unit impulse function or unit step function to represent this patterns of the series or patterns of these discrete values. So the third model is like you can graphically form this discrete signal. So using these three ways, you can basically explain any kind of a discrete signal, but most of the textbooks refer this first and second method, the graphical form and the mathematical form, to explain or demonstrate any kind of a discrete signal. Yes. Now, okay. So now we can think about, so we have a kind of a function xt, which is basically defined as a sine omega t, omega naught or whatever. So this omega is basically represent the angular frequency. So from omega, so you can easily evaluate the period of the signal. So from period, you can easily evaluate the frequency of the signal. So here t is a kind of a continuous random variable. So this is basically your continuous signal. So this is continuous signal. So how do you convert this xt to discrete signal? So this is your continuous signal. Now we are trying to convert it to a discrete form. So how do you do it? So what we can do, like we can easily convert this into a discrete signal. So this t is a kind of a continuous variable. Okay. So if you replace this t with this form, so this is, we'll put like this, otherwise it may be confusing. Okay, so t is now a continuous variable, and we basically convert this t to this form, n into ts. So this is called sampling period. And this is the integer variable. Now what we want is, like, we need to convert xt into the form of xn. So t is basically continuous and n is basically discrete. So t can take whatever the values in between minus infinity and plus infinity, but this n basically takes values between minus infinity and plus infinity, but they are basically integer values. So then we basically substitute n into ts instead of t. So then, for example, so then once you substitute this. Ts is a kind of a constant which we define it as a sampling period. So based on the sampling period, you may basically convert this continuous variable t into a discrete form. So for example, if you substitute this n value, so it becomes like this: ts 0, n is 0, then we have ts plus minus, so then we have 2 times ts plus minus 3 times ts plus minus 4 times ts, likewise for plus or minus infinity. So it means if you graphically draw it, so this is your t-axis, so this is 0, this is ts, so this is 2ts, 3ts, minus ts, minus 2ts, minus 3ts. So we basically pick the amplitudes at these points only. So it means we basically pick this one, so then we basically pick this one, so then we basically pick this one, this, like that. So this is 0, then this is ts, this is 2ts, this is 3ts, 4ts, 5ts. So likewise, so you can simply discretize this continuous variable t and simply pick this samples of the continuous signal. So initially we have continuous set of values. Once you discretize this function, continuous function xt, so you basically have set of samples. So then rather than xt, it becomes like nts. So we basically replace this xt with nts. T can be replaced by this. So then this is equals, if you substitute sine omega naught t is like nts. So ts is a kind of a constant for this process, and it's known as the sampling period. So this ts is the sampling period, and it's a kind of a constant for this particular process. So once you have a continuous signal, and if you want to make it a kind of a discrete form, so then you have to choose a sampling period. So it's up to you to decide based on certain requirements and constraint, but it's up to you to decide the sampling period. So once you select the sampling period, it's fixed and constant for this entire discretization process. So then we can basically simplify this like this: xn equals sine omega naught. Okay, so if ts is a kind of a constant, we can rewrite this one by simply dropping this ts, because this is a ts is a constant for this entire process, so we can simply ignore it from this variables. But there is a ts term there, but for the simplicity we can simply omit this ts and write the expression like xn equals sine omega naught n. So initially we start with this xt is sine omega naught t. Now we converted it to xn equals sine omega naught n. So see the difference. Here we have t, now we have n. So this is basically called sampling. Sampling the original xt. So how to take the sample? So you have to define the sampling period. So if you define the sampling period Ts, so you basically can get a discrete form of this xt. Yes. Now, so then you can plot the sine omega t and sine omega n. So if you refer the slide, third slide in this discrete Fourier series and transform, you can basically identify the difference between a continuous signal and a discrete time signal. So in left hand side, you can basically see the continuous signal sine omega t. So once you discretize, so once you sample it, so you can have this discrete form xn equals sine omega n in the right hand side. So by looking at this, you can see, like, if you want to develop the original continuous signal using this discrete form, there may be a kind of issue. So this is the issue, right? So let's think. So you take these samples. So this is your sinusoidal signal. So you basically take these three samples. Okay. So now this Ts is T by 2. So this is the period of the signal. So the sampling period is basically half of the period. So you can basically take this 0 point, then T by 2 and T. So you have three samples. Okay, so you have three samples. So if you want to construct, now your xn is something like that. So this is like x0. So this is x0. This is x1. This is x2. Ts would be T by 2. So this is your xn. Can you reconstruct this original sine omega t? So we basically have this xt, which is a sine function. So we basically run a process called sampling with a frequency of t by 2. T is the period of this original time domain signal. So then we'll end up with three samples at 0, then t by 2 and t. So this is actually x0. If we refer the time domain continuous signal, so this is the sample referred to this, and this is xt. So these are the three samples. So we basically ended up with three samples, x0, x1 and x2. So can we regenerate this original signal using these three samples? No. Okay. So we'll think of this. So now I'll link. So it means like so we feel like we don't have enough samples to construct this original signal. So now we'll try to increase the sampling free period. So reduce the sampling period to T by 4. So then we basically take this sample here 0. So then T by 4. So then this is T by 2. This is 3T by 4. This is T. Okay. So then we have basically 5 samples. One is here, the other one is here, this, this, this. So now this is your example. So we have 5 samples. In addition to the previous samples, we have these 2 samples coming from this peak values of the sinusoidal. So if you want to regenerate this original signal, what happens to this? So then we basically interpolate these two, interpolate the run the interpolation process to evaluate the samples in between these. So if you want to find a sample in between these two, so you just take these two and interpolate it. So by interpolating, so it means like we basically assume that linearity between these two samples. So this is your signal. So now ultimately you'll end up with this kind of a triangular type function rather getting a kind of a sinusoid. So it means still we feel like, so we don't have enough samples to take. So if we further make it small, t by 8, so then we have one sample here, one here, one here, here. So then ideally it would be like here, here, here. Then it's something like that. So if you interpolate it, like it's again a kind of a disk. So it is again a kind of a distorted version of this triangular form. So likewise, if you make the sampling period smaller and smaller, so we can capture more samples. So if this is the sampling period, we can define another parameter called fs, sampling frequency, which is actually one of these. Sampling frequency. Sampling period, capital TS, sampling frequency, simple fs. So once you make the sampling period smaller and smaller, so it means like your sampling frequency is getting higher and higher. So if you increase the sampling frequency, so it means like capture more samples. Okay. So by capturing more and more samples of the sinusoidal signal, you can basically take or regenerate the original XT. So for example, if you let the sampling frequency to infinity or the sampling period to 0, so we basically capture almost all the samples of the sinusoidal pattern. So then with these samples, you can basically get the original signal without any distortion. So from this, we can conclude that we should properly select the sampling period or frequency. So like for example, so we know that if we reduce your sampling period to 0 or close to 0, or if you increase your sampling frequency to infinity, so then you can capture infinite number of samples of, and you can easily regenerate this original signal. But the problem here is like if you increasing the number of samples, so then your discretization process is simply vanished. So then again, ultimately we'll reach into a kind of a continuous signal. If we consider this computer process, so if you basically, so this computer cannot manage this continuous signal. So what we basically do is we convert this continuous signal to a discrete form. So then if you refer this discussion we had now, so if you have three samples, let's assume like we need a kind of memory element to store this whatever the sample. So in the first case, when we are dealing with this sampling period of which is equals to t by 2, so we need to pack these three samples. So then we basically need three memory elements. So if we increase if you decrease your sampling period to t by 4, so we basically need 5 elements. T by 8, we basically need 8. 1 2 3 4 5 6 7 8 9 actually 9 samples. So if you increase this sampling frequency further and further, so then you will basically capture more and more samples, means you need more and more memory elements to store this samples. So then again, like once we consider the performance of the computing, so it basically degrade the performance. We need additional hardware to pack those information. We need kind of additional processing if you basically increase the samples to infinite. So then we should have a kind of a optimum place where you can define this. Once you define this optimum value of for the sampling period, it basically capture adequate amount of samples, and with that sample space we should manage to regenerate this original time domain signal. So this optimum value is the one which we are referring to. So with that optimum value, you can basically regenerate the original signal. Okay. So this is the thing what I want to initiate this discrete signal. So this is the major concern we need to clarify first. How we select the sampling period or sampling frequency. So once you select the sampling frequency and sampling period, so you can easily generate a kind of any kind of a discrete signal using this analog function. Okay. Then we can, so next time we'll discuss the few important factors regarding the sampling frequency or selecting sampling period. But so let's move to the discrete Fourier transform first. So we have this x omega. So this is minus infinity plus infinity xt e to the power minus j omega t t t. So this is the definition of Fourier transform for continuous signal. So now from this we can basically get the corresponding discrete form. So how do you get this discrete form? So we basically replace t using nts. Ts is the sampling period, n is the integer value. So then if this sampling period is a kind of a constant for the entire process, we can basically replace t with n. So then this is your x omega, which is the Fourier transform or the discrete Fourier transform. So this now we don't have any continuous function xt to integrate. So this integral is simply converted into a kind of a sum. So this is, so we basically remove this integral because xt is a continuous function, so we can have a kind of an integral form. If this xt is a kind of, so whatever the function you place it here is a discrete, so then this integral is simply replaced by a summation. So that's why we have sum here. So this xn now becomes a discrete function. So this t basically replaced with n, which is our discrete random variable omega n. So this is the discrete Fourier transform. This is discrete Fourier transform. So this is the Fourier transform of a continuous signals. Once you convert it to a discrete form, so you have this discrete Fourier transform. So then this is your discrete function, discrete signal. So by looking at this discrete signal, we know that so discrete signal xn can be defined from minus infinity to plus infinity, but this n is basically taking integer values only. So depending on the number of samples, this may be a kind of a infinite length sequence or kind of a finite length sequence. So infinite length sequence means, so the number of samples is basically infinity. Finite length sequence means you can basically have finite set of samples to express xn. So this is a kind of a, so this is a finite length sequence. So the length is basically 4. So we have 4 samples there. So if it is infinite, so un is basically infinite sequence. So depending on the length of the sequence, we can simply cluster it or group it to 2. So one is the finite length sequence, the other one is the infinite length sequence. So for the finite length sequence, we have finite set of samples for the xn. If it is infinite set of sequence, so you basically ended up with infinite number of samples. Okay, so next time we move to the sampling process. How do you manage to reconstruct this original signal by properly defining the sampling frequency or sampling period? Then based on that, we can define the fundamental frequency or fundamental period of the signal, and then move to the properties of this discrete Fourier transform, and we'll try to go through a couple of examples. Okay, for the today, so we'll stop at this point and we'll move to the next section.